A very good morning and welcome to my course Basic Physics. This course is generally made for diploma degree students of first year, first semester. Now the course pages are www.webscte.org and www.webscte.co.in. So students, the syllabus for this subject Basic Physics is already uploaded in the State Council website. So if you want, you can directly download the syllabus for your first semester, first year curriculum, and from there you can easily find out the sub-syllabus for physics, basic physics. So the title of the course is Basic Physics. It is under the category of Basic Science course, and it has a credit 2 lecture per week and 2 practical per week. So this course is generally made for diploma degree students of first year, first semester. So all the branches except architecture, photography, multimedia and printing technology. So apart from these 4 departmental students, rest of the departments have to study this basic physics as a part of their first year, first semester curriculum. Students, as we have our college only electrical and electronics and communication, these 2 departments. So these 2 departmental students will have to study this basic physics as a part of their first year, first semester curriculum. Now the topic that I will going to discuss today, that is photometry, which is related to light. So which includes luminous flux, luminous intensity, illumination and their SI unit, and principle of photometry, the statement only. So these all topics are under unit 4, that is light. So prerequisites for these topics are basic mathematical knowledge to solve problems on numericals, and knowledge of basic concept science such as physics. Course objectives are learn the use of photometry, that is luminous flux, luminous intensity, illumination and also their SI units. Okay, so after completion of this course, students will able to know what is the unit of luminous flux, what is the actual quantity, physical quantity that defined by the luminous flux, luminous intensity, illumination, and what is the principle of photometry and its applications. So these are considered to be as a corresponding course outcome. Now before going to start today's topic, hope all of you have understand all the video lectures or lesson that I have already uploaded, because before starting with the today's topic, that is basically photometry, you need to know what is unit and dimension. Okay, so those who have missed that class, please go through that video once again, so that it will be very easier for you to understand the photometry and corresponding unit that today I will going to be discuss. Now before starts with photometry, what is light? You need to know what is light. So as per your knowledge, you know that light is a form of energy. Okay, so as light is a form of energy, you cannot be create that energy or you cannot destroy also. So that means you can convert this light energy into another form, that is possible, but it is not possible to create or destroy the energy permanently. So as it is a form of energy, so it may be possible that in some place that energy value will be maximum and in some place that energy value will be minimum. So corresponding the intensity of light will be maximum, intensity of light will be minimum. Okay, so the distribution of light energy is very much important. Now in practical situation in daily life, you can see that when you consider a tube light, okay, it emits light, okay, but that value is countable and you can easily see towards that tube light. But if it is a halogen light, it won't be possible for you. Why? Because these two are also a light source. One is tube, another one is halogen bulb. Now the problem is that the intensity or energy for that halogen light is much more with respect to the tube bulb. Now how you count or how you will measure that amount of light emitted by that two source, different source? So you need to know by which quantity or by which phenomena or by which unit you can differ this amount of measurement of light. So these things are actually also discussed in details in this chapter, photometry. And photometry is basically related with the measurement of light that I will going to discuss in details. So next, light is energy, you know. Light is also considered as electromagnetic wave. So in that means light must follow some characteristics, must follow some principles. Okay, so in relating with that, here as we considered light is a particle, light is also a wave. So here as per the particle property of that light, so that means you know that light consists of a photon, okay, so which considered as a packet of quanta, that is E equals to h, which emits light. So now we will discuss how you will measure that light. So what is photometry? Photometry is the science of the measurement of light in terms of its perceived brightness to the human eye. It is distinct from radiometry, which is the science of measurement of radiant energy, including light also, in terms of absolute power. In modern photometry, the radiant power at each wavelength is weighted by a luminosity function that models human brightness sensitivity. So typically this weighting function is the photonic sensitivity function, although the scotopic function or other function may also be applied in the same way. So as I have already discussed that you can easily distinguish between the light coming from a tube source and coming from a halogen light source. Okay, so by using your eyes you can easily distinguish between these two. Why? Because the amount of brightness, amount of light that coming out is completely different. Okay, So that means your eye plays a very important role in case of photometry, or in case of measurement of the brightness of the source that emits light. So the human eye is not equally sensitive to all wavelengths of visible light. So photometry attempts to account for these by weighting the measured power at each wavelength with a factor that represents how sensitive the eye is at that wavelength. So the standardized model of the eye's response to the light as a function of wavelength is given by the luminosity function. Now the eye has different responses as a function of wavelength when it is adapted to the light conditions. So that means photoscopic vision and dark condition, that is scotopic vision. Photometry is typically based on the eye's photoscopic response, and so photometric measurements may not accurately indicate the perceived brightness of source in dim lighting condition where colors are not distinguishable, such as under just moonlight or starlight. So photopic vision is characteristic of the eye's response at luminance level over 3 candela per square meter. So scotopic vision occurs below 2 into 10 to the power minus 5 candela per meter square. Mesoscopic vision occurs between these limits and is not well characterized for spectral response. So that means there is a range which is play a very important role. So within that range it is possible or permissible for the human eye to respond as per emitting source or emitting light, okay, that coming from any source. Now here so SI units of photometric quantities and dimension I have given in a chart. Okay, so from this chart you can see the name of the physical quantity, the symbol represents that physical quantity, corresponding units is given there, then the corresponding symbols of the unit is given there, next the dimension and the details note regarding each of the physical quantity that represents the photometric quantities. Next, so the first one, it is called luminous energy. In photometry, luminous energy is the perceived energy of light. So this is sometimes called the quantity of light. So luminous energy is not the same as radiant energy, the corresponding objective physical quantity. So this is because the human eye can only see light in the visible spectrum and has different sensitivities to light of different wavelengths within the spectrum. When adapted for bright conditions, so bright conditions means that is photopic vision, the eye is more sensitive to light at a wavelength of 555 nanometer. So you know 1 nanometer is equals to 10 to the power minus 9 meter. So here 555 nanometer, that means 555 into 10 to the power minus 9 meter. Now light with a given amount of radiant energy will have more luminous energy if the wavelength is 555 nanometer than if the wavelength is longer or shorter. So light whose wavelength is well outside the visible spectrum has a luminous energy of 0 regardless of the amount of radiant energy per cent. Okay. Next one is luminous flux. In photometry, luminous flux or luminous power is the measure of the perceived power of the light. It differs from radiant flux, the measure of the total power of electromagnetic radiations including infrared, ultraviolet and visible light. In that, luminous flux is adjusted to reflect the varying sensitivity of the human eye to different wavelengths of light. So the SI unit of luminous flux is lumen. So 1 lumen is defined as the luminous flux of light produced by a light source that emits 1 candela of luminous intensity over a solid angle of 1 star radian. So in other system of unit, luminous flux may have unit of the power. Next one, that is luminous intensity. In photometry, luminous intensity is the measure of the wavelength latent power emitted by a light source in a particular direction per unit solid angle based on luminosity function, a standardized model of the sensitivity of a human eye. The SI unit of luminous intensity is candela, and SI base unit, like other SI base unit, candela has an operational definition. It is defined by the description of a physical process that will produce 1 candela of luminous intensity. So by definition, if one constructs a light source that emits monochromatic green light with a frequency 540 Hz and that has a radiant intensity of 1 by 683 watt per star radian in a given direction, that light source will emit 1 candela in the specified direction. So what is luminance? Luminance is a photometric measure of the luminous intensity per unit area of light traveling in a given direction. It describes the amount of light that passes through, is emitted from, or is reflected from a particular area and falls within a given solid angle. So these are the basics of luminous intensity and luminance. So that means you can define the luminous intensity by the unit candela. Next one, illuminance. In photometry, illuminance is the total luminous flux incident on a surface per unit area. It is a measure of how much the incident light illuminates the surface. Wavelength weighted by the luminosity function to correlate with human brightness perception. Similarly, the luminous emittance is the luminous flux per unit area emitted from a surface. So, luminous emittance is also known as luminous existence. Next one is luminous exposure. In photography, exposure is the amount of light per unit area, the image plane illuminance times the exposure times. So, reaching a frame of photographic film or the surface of an electronic image sensor as determined by shutter speed, lens aperture and scene luminance. So, exposure is measured in lux second and can be computed from exposure value, and scene luminance is a specified region. Now, what is luminous efficacy? Luminous efficacy is a measure of how well a light source produces visible light. It is the ratio of luminous flux to power measured in lumen per watt in the International System of Units SI system. So, depending on context, the power can be either the radiant flux of the source's output, or it can be the total power, electrical power, chemical energy, or it may be any others consumed by the source. Which sense of the term is intended must usually be infrared from the context and in sometimes unclear. The former sense is sometimes called luminous efficacy of radiation, and the later luminous efficacy of a source or overall luminous efficacy. Luminous exposure. What is the meaning of luminous exposure? In photography, exposure is the amount of light emitted per unit area. So that thing I have already discussed. I don't want to repeat that. This is almost the same of luminous exposure. Next one. This is basically the last part and the most important part of principle of photometry. Now, this principle of photometry, it states that if two sources produce equal illumination on a surface, then the ratio of the luminous intensities of the two sources is equal to the ratio of the square of the respective distances of the two sources from that surface. Let E1 and E2 be the intensity of illumination due to the source of luminous intensity I1 and I2. The corresponding distances R1 and R2 from the sources to illuminating surface is so adjusted that the two sources produce equal illumination, so that you can say that intensity of these two must be equal. It means E1 will be equals to U2. Now that you can put the value of that intensity, so it will be I1 by R2 R1 square is equals to I2 by R2 square, or I1 by I2 is equals to R1 square by R2 square. So that means you can write that intensity of the illumination is directly proportional to the square of the distance between them. So here I is directly proportional to R square. So this is the basic principle of photometry, and there is a lots of applications are also there on this principle, but as per your syllabus you only have the statements of the principle of photometry. So here I have discussed only the statements. Now these are the books that you considered as reference books, and you can practice lots of short questions or numericals from these books. These are the will be very helpful if you practice lots of questions, or at least the last 5 to 10 years question from these books. Now the evaluation process are same. The students have to appear for a mid-semester exam of 20 marks, and attendance, assignment or interaction that consists of 10 marks. So internal will be total of 30 marks, and the end semester exam they have to appear for 70 marks question. So today I have discussed on this chapter photometry, that is related to light. Hope all of you have enjoyed and understand. So thank you.